Hi everyone. So in today's video, we're going to be talking about a new method for taking derivatives. And it's going to use a lot of the ideas that we've built up so far in the quarter, but it will basically allow us to take the derivative of different types of equations that are different from the ones that we've been working with so far. So before we get into the actual method of taking these derivatives, I want to talk about the types of equations that will require us to use this method. So we're going to be using implicit differentiation when we have something that's called an implicitly defined curve, which sounds a little fancy, but it's not really that complicated. So I'll give you the full definition in a second, but I first just want to focus on this word curve. So the word curve in the context of math, it's basically just a way of saying a graph. And the reason that I'm using the word curve and not function is because curve is a more general word that includes graphs that are not necessarily functions. So for example, a circle is not a function, right? It fails the vertical line test. However, it is a curve, or a sideways parabola is not a function, but it is a curve. So curve is just, think of it as a word for graph. And it could be a function, but it's not necessarily a function. So basically you use that word when you want to describe a graph in the most general terms, but you're not sure whether you're talking about a function or not, so you just use curve as kind of a catch-all term. So an implicitly defined curve is a graph, and it's a graph that's described by an equation relating x and y. So when you think about the types of equations that we're used to graphing, things like y is equal to x squared, or y is equal to sine of x, or y is equal to 3x plus 5. Those are all equations relating x and y. However, if it's an implicitly defined curve, it's going to be an equation that relates x and y without being in the form f of x is equal to something or y is equal to something. Basically, like the x's and y's are going to be kind of blended together. So I'm just going to say that like this, not in the form y is equal to f of x. And I think if you're unclear what I mean by that, we'll look at some examples in a second, and I think that will become a lot clearer. So in other words, the way you can kind of think about it is that the x's, oops, that was supposed to be an S. The x's and y's are kind of blended together. So we have these equations where it's not like y is equal to 2x plus 5. You have x's and y's kind of on the same side of the equation, kind of mixed together. And you cannot solve for y. Okay, so let me write down some examples of what these kind of equations might look like. So examples of, so I'm going to first list some that are implicitly defined curves. So one example, kind of the first most basic example would be something like x squared plus y squared is equal to 25. So that's a circle, right? And so why does this fit the definition that we have above? Well, it's an equation relating x and y, right? It's telling you a relationship between x squared and y squared equaling 25. However, it's not written in the form f of x is equal to or y is equal to. It's all kind of blended together. Another example would be x cubed plus y cubed is equal to 6xy. Another example would be sine of x plus cosine of y is equal to 1. Another example, I'm just going to throw out like two more, would be sine of x plus y is equal to y times cosine of x. And one last example would be e to the y times plus cosine of y is equal to x cubed. So basically any kind of equation where you're kind of just putting x's and y's together in some way where you can't actually solve it for y and write it as y is equal to a function of x. So if you can solve something and write it as a function of x, that would be called an explicitly defined curve. And if it's an explicitly defined curve, well, then you could just call it a function. So examples of that would be things like y is equal to x squared, or f of x is equal to sine of e to the x plus 1, or y is equal to the square root of x plus 5. Those are all explicitly defined curves. And why are we using the word explicit? Well, it's like you can explicitly say, okay, y is equal to this, f of x is equal to this. Whereas the implicit ones, because the x's and y's are kind of blended, you just can't explicitly say, what is y in terms of x. You have to define it instead in this kind of blended up way. So I want to take a minute to look at some of the graphs of these implicitly defined curves because they can make some really interesting shapes, and I think it's kind of fun to play around with them. So first of all, here we have the first graph, which is x squared plus y squared equals 25. So this one should be familiar to you. This is a circle with a radius of 5. So one thing I want to point out about the way that implicitly defined curves work is that whatever the equation is, it's still, so when you have a function, right, if you have like f of x is equal to x squared, you can find points that lie on your graph by just plugging in a particular number for x and then seeing what you get for y. And because implicitly defined curves are not set up in the form y is a function of x, that same methodology doesn't really work. However, it is still true that any point that lies on your graph satisfies your equation. So for example, the point 3, 4 is on our graph, right? So 3, 4 is on our graph. And why is that? Well, the equation for this graph is x squared plus y squared is equal to 25. And I'm not sure if the way that I have the screen recording set up, I'm not sure if you can see the entirety of this equation, but it says x squared plus y squared is equal to 25. So if we plugged in 3 for x and 4 for y, we would get 3 squared plus 4 squared, which is 9 plus 16, which is 25. And so that's why the point 3, 4 lies on our graph. The point 5, 0 also lies on the graph because if you plug in 5 for x and 0 for y, you get 5 squared plus 0 squared is equal to 25. So every single point, even the ones that are not sort of like super nice clean points, so like whatever is this point here, also if you were to plug in the x value for x, the y value for y, you would get a true statement when you plug them into the equation. So let's look at some of the more kind of funky of these graphs. So this one is x cubed plus y cubed is equal to 6 times x times y. So this is called the folium of Descartes. It has like a fancy name. Again, just like the circle, see how this one is not a function of x. So if you were to try to draw a vertical line, it would pass through the graph more than once. And then when we get into these next ones, you'll see that some of them are kind of even more repetitive or like they fail the vertical line test even worse, right? So if you were to draw a vertical line at x is equal to 1, it would pass through this graph 3 times, right? But let's look at this next one. So this is sine of x plus cosine of y is equal to 1. And this graph is just like infinite polka dots. So this is very, very clearly not a function of x. And let me just show you how we can kind of make sense of some of the points that lie in this graph. So I'm going to change the axes so that they're labeled with in terms of pi instead. So for example, it looks like the point pi over 2, pi over 2 lies on the graph. So why is that? Well, if we plug in pi over 2 for x, that gives us sine of pi over 2. And if we plug in pi over 2 for y, that gives us cosine of pi over 2. Sine of pi over 2 is 1, cosine of pi over 2 is 0, so together we get 1 plus 0 is equal to 1. So the point pi over 2 comma pi over 2, when you plug it into the equation, you get a true statement. And you'd get the same idea if you tried to plug in 0. So 0, 0, 0. If you take sine of 0, that's 0. Cosine of 0 is 1. 0 plus 1 is 1. Or if you go to the point pi comma 0, that would be now plugging in pi for x. So you'd be doing sine of pi, which is 0, plus cosine of 0, because that's the y-coordinate, is 1. And so 0 plus 1 is 1. So any point that you pick on your graph, when you plug it in, is always going to give you a true statement. And the reason that this graph repeats so much is because trig functions repeat their values, right? So because trig functions are so repetitive, if you have certain points that work within this kind of smaller range, of course you're going to have even more points that work when you look at how the graph kind of repeats itself later on. Okay, so next one is sine of x plus y is equal to y times cosine of x. So this one's kind of interesting. We've got these kind of repeating waves. Next one is e to the y plus cosine of y is equal to x cubed. I think this one is particularly interesting. And then one thing that I think is kind of cool about implicitly defined curves is, and let me just change this back to being kind of regular numbers. One thing I think is kind of interesting about implicitly defined curves is that if you just kind of play around a little bit with like throwing in different x's and y's different places, you can get really interesting equations. So like, for example, actually just one small change. Let's change this x cubed to being instead x squared. And all of a sudden we have a totally different shape of graph. Or, let me put it back to being x cubed. If I make this now e to the x times y, that now gives me some very different kind of interesting shape going on here. We could try multiplying this by x. That would give us something totally different. We could try multiplying this by sine of x, and we get something really crazy here. And what's going on here, the reason that's all scattered is basically it's really hard for the computer to calculate points that lie on this graph because it's a rather complicated equation. And so Desmos is just kind of struggling to keep up with finding points that lie in the graph. But if we zoom in, we can see that there's something pretty crazy going on over here. So I just think it's kind of fun to play around with these. I think like if you ever see people kind of drawing graphs on Desmos, like drawing smiley faces or other kind of shapes, they're usually going to be using implicitly defined curves. I feel like I came up with one earlier that was really cool, but now I don't remember what it was. What was it? Maybe I don't know. I forget. I had one that was cool and I was all ready to show you, but now I forget. Maybe let me try one thing. Oh yeah, well, that wasn't it, but that's kind of interesting. Yeah. Anyway, long story short, implicitly defined curves are cool. And yeah, let's now try to talk about how we're going to take the derivatives of them. So why do we need a new method for taking derivatives of implicitly defined curves? Well, it's basically because all of the rules that we know so far only work when we have functions like the ones that are listed here in orange, right? We have derivative rules that So why do we need a new method for taking derivatives for things that look like x squared plus y squared is equal to 25 or sine of x plus cosine of y is equal to 1? Basically, it's because all of the derivative rules that we have so far only work when you have something that is a function of x, or it could be a different variable, but things like the ones that are listed in orange here, right? We know how to take the derivative of x squared. We know how to take the derivative of sine of e to the x. We know how to take the derivative of 1. We know how to take the derivative of x square root of x plus y. And we kind of like apply those rules only to one side of the equation, right? And then we just say, okay, y prime is equal to 2x, or f prime of x is equal to whatever derivative you get. So in the cases where the x's and y's are kind of blended together, that kind of rationale just doesn't really make sense. You can't just say, oh, the derivative of this is that, because the x's and the y's are kind of blended together. So I want to go through an example, kind of a simple example to start with, and we're going to kind of use this as an example to also write down a list of generally how we'll approach these implicit differentiation problems. So I'm going to kind of write down some steps, and then as we go through this, we'll kind of go through the steps for this specific example. So let's say that we wanted to, for example, find dy dx for the equation x squared plus y squared is equal to 25. So that's the circle that's graphed here, right? Circle with a radius of 5. Okay, so the first step that we're going to do is we're going to take the derivative, we're going to take d dx of both sides of our equation. So whatever equation it is that is defining your implicitly defined curve, you're going to take that derivative of both sides. So in this case, we have d dx of x squared plus y squared is equal to d dx of 25. So just like, in algebra, you do one thing to both sides of the equation, it's the same idea. We're just we're performing an operation on both sides of an equation. Now, because of how derivatives work, we can now split this up into the derivative of, I don't know where that e came from, derivative of x squared plus the derivative of y squared, and then the derivative of 25. So the next step is basically for any term not containing y, you can take the derivative normally. And so when I say normally, I just mean the same way that we've been doing all along. Derivative. So in this case, what does that mean? That means that when we take the derivative of x squared and the derivative of 25, the same derivative rules that we've used all along are going to apply. So we can say the derivative of, or let me just replace it with the derivative. So the derivative of x squared is 2x. So we have 2x plus, and then we'll talk in a moment of how to deal with this next part, the derivative of y squared, because that one does have a y. And then what's the derivative of 25? Well, that's 0. Okay, so the kind of tricky part, and you'll definitely get the hang of this after you've done some practice, but it's a little hard to explain. But yeah, so the next thing we have to work with is how to take the derivative of y squared. So when taking the derivative of a term containing y, I always do that with the word containing y, what we're going to have to do is we're going to have to use the chain rule. And this is probably initially going to sound confusing, but once we do some examples, I think it'll make more sense. We're going to use the chain rule with the inner function being y. And I know that probably sounds like nonsense, but we'll do this example in a second. So basically the idea is that when you have something like y squared, that's like you're doing something to y, right? So you can kind of think about what are you doing? You can think of that as the outside function. So in this case, if the function we're looking at is y squared, well, the outside function is the squaring part, right? So let's write that down here. So for d dx of y squared, the outer function, and let me actually use a couple different colors here. So let's say this, y squared. So the outer function is going to be u squared, right? Because it's the function, it's the squaring function. That's what you're doing to y. And then the inner function is going to be y. So I'm just going to kind of do like a side example for a second, just to kind of remind you how the chain rule works. And I think it might kind of help to understand how this derivative is going to work. So this is like totally a side example, completely different function. But let's say that, for example, you were going to take the derivative of sine of x squared. Right? That's usually written as sine squared of x, but I'm just writing it like this. So the derivative of sine of x squared, you would say that the outer function would be u squared, right? Because it's the function where you're taking something and you're squaring it. And then the inner function would be sine of x. And so what would the derivative come out to be? The derivative would be equal to, you would bring down the 2 and kind of use the power rule to do the outside derivative. So you would get 2 times sine of x, and then you would multiply by the derivative of the inside function. So this is your outer derivative, and this is your inner derivative. So you're kind of using the power rule on the outside part, and then you're multiplying by the derivative of the inside part. And so this function above is going to be exactly the same. Or I shouldn't say exactly, but it's going to be very similar. So if the outer function is u squared, well, when we take the derivative of that, we get 2 times u, right? So d dx of y squared is going to equal 2 times u, which we can then replace the u with y, right? Because just like in the example I just erased, when you're doing the outside part of the derivative, you leave your original inside function where it is. So we're leaving the y where it is. Then we're supposed to multiply by the derivative of y. And we don't really like have much information about y, right? It's not like sine of x where you know what the derivative is. So what we do instead is we literally just write dy dx. So this is our outer derivative. And this is our inner derivative. So this is the way it's always going to work when you're taking the derivative of something involving y. You're going to kind of like do the derivative quote unquote normally. So, you know, the derivative of y squared, you would probably guess would be, 2 times y. But then you always have to multiply it by dy dx because basically we're kind of considering y as a function of x in this context. And I know that's a little confusing because in general, and like if we look at this graph, y is not a function of x in this picture. However, the basic idea is that if you were to just kind of separate the circle into pieces, you could have a piece where y is a function of x. And I really don't want to get too into that because it actually gets pretty complicated, and to be able to explain it well kind of goes beyond the scope of this class. So this is going to be one of the few times in this class where I feel like I'm not going to be able to kind of get to the bottom of explaining something completely. I'm just going to ask you to kind of trust that this works and that you're always taking the outside derivative by just kind of doing normal derivative rules to y, and then you're always going to multiply by dy dx as that inside part of the chain rule. So maybe let me add that to our list of kind of steps here. So the inner function being y, and its derivative, so I'll just say this, I'll just say inner derivative, you're always going to write as dy dx. Or you can write y prime. I'm going to write dy dx for the first few examples because I like how it kind of fits with the fact that we're taking d dx of both sides. But later on, once we get more comfortable with like the meaning of what we're doing here, you can just use y prime if you want, because it just kind of makes your equations look a little bit nicer than having to write dy dx. Okay, so let's put this back together with what we had, right? So we took the derivative of both sides of the equation, and so we got 2x, and then right now we just took the derivative of this part, so we can fill that in now, and then we have is equal to 0. So we got 2x plus 2y times dy dx is equal to 0. So the next step, which is kind of different from typical derivatives, is that you're then going to solve for dy dx, right? Because that's what we're looking for. We're looking for dy dx. So in this case, how would that work? Well, if we subtract 2x from both sides, we get 2y is equal to 2y times dy dx is equal to negative 2x. And then we can divide both sides by 2y. So we get dy dx is equal to negative 2x over 2y. And that simplifies to negative x over y. So our final answer is that dy dx is equal to negative x over y. So one thing I want to point out here is that this derivative is very different from the ones that we're used to, because it doesn't just have x's in it, it also has y's. And that kind of makes sense because our original equation was also a blend of x's and y's. So what we'll find in general is that when you take the derivative of an implicitly defined curve, you're not going to get, f prime of x is equal to. You're going to have dy dx is equal to, and then the right-hand side of your equation is going to have both y's and x's. So going back to, or maybe let's try to think about what the derivative tells us. So the derivative is not a function of x, as we mentioned, and actually you can't graph this. And the reason you can't graph it is because if you think about it, it actually has 3 variables. So it has x and y, and then whatever you get as the slope would be a 3rd variable. And so if you were to try to graph this, you would have to actually graph it in 3 dimensions, not 2. So we're not going to be looking at the graphs of the derivatives, but we will still be able to see what the derivatives tell us about the original graph. So just like with regular derivatives, the derivative of a implicitly defined curve tells you the slope. So let me write this down. This tells you the slope of the line tangent to the graph x squared plus y squared is equal to 25 at a point x comma y. And so one thing that is a little bit different from other derivatives we've worked with is that you need to plug in both x and y in order to find that slope. So for example, let's say that we wanted to find the slope of the line tangent to x squared plus y squared is equal to 25. Let's say we wanted to find the slope at the point 3, 4. So how would we find that? We would plug in, we know dy dx is equal to negative x over y. And so we would plug in 3 for x and 4 for y, and we would get negative 3/4. So I just want to quickly point out, why is it that we need to plug in both an x and a y value? Well, let's look at the graph. So if I had just told you to find the slope of the tangent line at x is equal to 3, there would be two different points, right? There's two different points on this graph at x is equal to 3. And they have different slopes, right? If you were to sketch the slope of this one, it's negative. If you sketch the slope of this one, it's positive. And so basically you need to plug in both the x and the y coordinate to know for sure what that slope is. So for the one that we just did 3, 4. So this one we saw had a slope of negative 3/4. What if we did now instead 3, negative 4? So if we now do the tangent line at 3, negative 4, well, then we would get dy dx is equal to negative x over y. So that would be equal to negative 3 over negative 4, which would equal to positive 3/4. And so looking back at the graph, that kind of makes sense because the circle has a lot of symmetry. Well, the point that is the one with the negative slope, this point straight below it, it looks like it should have the same slope, but just positive. So just like with regular quote unquote derivatives, we can find the slope of a tangent line. It's just that with these ones, you have to plug in both an x and a y value. Other thing, and I don't think we'll do an example of this in today's video, but if you were asked to find an equation of the tangent line, it's exactly the same as any other equation of a tangent line you've ever found. Once you know the slope and you know a point it goes through, you can just write down the equation of the line. So for example, if you were asked to find the equation of this tangent line here, you would know that it had a slope of negative 3/4, and you would know that it went through the point 3, 4. So there you go. That's all the information you need in order to write its equation. So we don't really need to do that as like a whole separate new thing. It's really the same thing we've been doing all along. It's just that the method for finding the slope is a little bit different now that we're dealing with implicitly defined curves. Okay, so I want to do like 2 more examples. And by the way, this is a topic that can definitely get a little tricky. So we're going to be sticking to pretty simple examples today and then getting into some more complicated examples next week. So this is the graph of, so this one is sine of x plus cosine of y is equal to 1. So what we're going to do is we're going to find dy dx for the curve sine of x plus cosine of y is equal to 1. So let's start by doing that, and then at the end we'll also find the slope at a particular point. So the first step we're going to do is we're going to take the derivative of both sides, right? We're going to do d dx of sine of x plus cosine of y is equal to d dx of 1. So now we can break this down and take the derivative of each piece. So we're taking the derivative of sine of x, we're taking the derivative of cosine of y, and then the derivative of 1, well, that's just equal to 0. Okay, so as we saw in the last example, when you take the derivative of something that is only contains x's, it's the same kind of derivative we always do. So the derivative of sine of x is going to be cosine of x. And then this next part, well, the derivative of cosine of y, we're going to first do our outer derivative. So the outer derivative would be negative sine of y. So we're just taking the derivative of kind of the outside part and ignoring the fact that it's a y on the inside instead of an x, just sort of normally taking the derivative. But then we have to remember that we have to multiply it with dy dx at the end. And so the last step is to solve for dy dx. So we're going to isolate the dy dx part. And so we can accomplish that by subtracting cosine from both sides. So if we subtract cosine from both sides, we get negative sine of y times dy dx is equal to negative cosine of x. And then if we divide both sides by negative sine of y, we get dy dx is equal to negative cosine of x divided by negative sine of y, which is the same thing as cosine of x over sine of y. So let's try to find the slopes of the tangent lines at a couple of specific points. So let me nudge this one down a little bit. So let's say that now we wanted to find the slope of, we're going to do a couple of different tangent lines. So the tangent lines at, let's do the point pi over 2, pi over 2. So we talked about in a little bit earlier, we talked about how you could see how that point lies on the graph. And then the other point we'll do is pi 0. So we can see that both those points lie on our graph. So for the first part, so if we're trying to find pi over 2 comma pi over 2, we have dy dx is equal to cosine of pi over 2 divided by sine of pi over 2. So how do you find cosine and sine of pi over 2? Well, if you think about on the unit circle, going to an angle, that is not a circle. Let's try that again. So if we think about going to an angle of pi over 2, the x coordinate is 0 and the y coordinate is 1. And so that means that sine of pi over 2 is 1 and cosine of pi over 2 is 0. So we get 0 divided by 1, which is 0. And let's look at our graph. So we're looking at the point pi over 2, and that seems like that is the correct slope, right? It has a slope of it's horizontal, so it has a slope of 0. So next we're going to do the point at pi comma 0, and looking at this point, we might already guess the slope looks like it's going to be undefined, right? Because vertical lines have an undefined slope. But let's see what happens if we plug that into our equation. So if we plug in, so we're plugging in, so here's our original dy dx, and we're plugging in pi as our x value. So we have cosine of pi on the top. And then in the denominator, we have sine of 0. So cosine of pi would be going to an angle of pi. And so that's -1, 0. So that means cosine of pi is -1. And then sine of 0 is an angle of 0. And that has a y coordinate of 0. So sine of 0 is 0. And what's -1 over 0? Well, that is undefined. And that makes sense because we see in our picture that the tangent line at that point is vertical. So the slope is undefined. Okay, so we're going to do one more example, and this last one is a little bit trickier in terms of the kind of algebra that goes on. So we're going to do find dy dx for, and I'm going to write this a little differently than I wrote it earlier. So I'm going to write it as e to the y. Sorry about that pop-up. So we're doing e to the y is equal to x cubed minus cosine of y. So earlier when we looked at the graph, I wrote it as e to the y plus cosine of y is equal to x cubed. I just rearranged it because I think it will introduce something a little more interesting in the process of doing this. Okay, so we're going to start by taking the derivative of both sides. So we're going to take the derivative of both sides with respect to x. So we have e to the y on the left-hand side. And then on the right-hand side, we have the derivative of x cubed minus cosine of y. So on the left-hand side, this is one of the ones where we're going to have to multiply by dy dx, right? Because there's a y in it. So again, I would just think of like a separate chain rule example. Like let's say you were taking the derivative of e to the sine of x. So totally separate, not related to this question, just want to do a side example. Just because I think it's a little easier to see how the chain rule works in examples like this. So how would the chain rule work here? Well, the outside part of the derivative would be e to the sine of x, right? It would leave that exponent the same because it's like taking the derivative of e to the u, and the derivative of e to the u is just e to the u. And then you multiply by the derivative of the inside function, which is in this case the exponent. So you'd multiply by cosine of x because that's the derivative of sine of x. In this example, our outer function is again e to the u, and so the first part of the derivative is just going to be e to the y. But then we need to multiply by the derivative of the inner function, so we have to multiply by dy dx. And then on the right-hand side, we have the derivative of x cubed. So that's just going to be 3x squared. It's just a normal derivative. And then when we get to the derivative of cosine of y, we're first going to take that outside derivative. So the outside part of the derivative would be negative sine of y, right? We're just taking the derivative of the cosine part. I'm leaving the input the same. And then we have to multiply that by the derivative of the inside function, which is dy dx. So altogether, we have e to the y times dy dx is equal to 3x squared plus sine of y times dy dx. So we're trying to solve this for dy dx. There's one thing that's a little bit different here, which is that we have dy dx's on both sides of the equation. So this might be an example where you might want to rewrite dy dx as y prime, and you're welcome to do that, like moving forward, just because I think it somehow just makes the algebra like look a little less scary when it's not dy dx, even though you're just replacing it with a different symbol. So how are we going to go about solving something like this? Let me just do, again, kind of an unrelated side example. Let's say you were trying to solve something that looked like 5x is equal to 3 minus 7x. And you're trying to solve that for x. What would you do? You would want to gather all your x's to one side, right? So you would add 7x to both sides and go from there. And so it's the exact same idea here. It's just that we're going to try to gather up our y primes because that's what we're trying to solve for. So if we, let's subtract, you could do it either way, but let's subtract this part to the left side. So we're going to subtract sine of y times y prime to both sides. So we get e to the y times y prime minus sine of y times y prime is equal to 3x squared. So where do we go from here? Well, now we have two things that both have a common factor of y prime, so we can factor out y prime. So why is that useful? Well, if we factor out y prime, we're left with e to the y minus sine of y is equal to 3x squared. And so keeping in mind that our goal was to solve for y prime, we can now divide both sides by e to the y minus sine of y. And there we go. That's it. So again, all we did here that was different is we replaced dy dx with y prime because they mean the same thing. And again, the reason that I tend to stick with dy dx at the beginning is because it kind of matches better with this notation. It helps you remember that you're taking the derivative with respect to x. You're treating x as your input variable, as your kind of normal variable, whereas y you're kind of treating differently. But you're welcome to just write y prime instead because I just think it makes things look a little kind of cleaner and calmer. And then what was different about this from the other examples? Well, we had to move we had multiple terms containing y prime, and we had to move those to one side and then factor out the y prime, because that's what allowed us to then ultimately isolate y prime. So one last question here, which is, again, let's try to find a slope of a tangent line. So let's say we wanted to find the slope of the tangent line at the point, and hopefully I have this right. So I think the point was cube root of 2. I'll write it as 2 to the 1/3. I'll write it as cube root of 2, comma 0. I believe that's the right point. So that would be this point here on our graph. So how does this work? Well, we know what y prime is, so we can just plug that number in, or those numbers in. So on the numerator, we're going to get 3 times the cube root of 2 squared. And then in the denominator, we're going to have e to the 0 minus sine of 0. So let's simplify the denominator first. So e to the 0 is 1, sine of 0 is 0, so the denominator is just 1. And then the numerator, well, we can maybe write, you could type this into a calculator to get an approximation, but if you wanted to kind of write this a nicer way without typing into a calculator, so maybe actually let's write it as a fractional exponent. So the cube root of 2 is the same as 2 to the 1/3, and then we're squaring that. So what happens when you take an exponent and raise it to another power? You can multiply your exponent. So this is the same as 2 to the 2/3. And then additionally, one more step you could take is 2 to the 2/3. Well, we can square the 2. So we can rewrite this as 3 times the cube root of 4. And I don't want you to get too caught up in all of that. I know that was probably some arithmetic / simplification that you're not used to, so I wouldn't worry too much about that. But yeah, let's see. I'm just typing it into my calculator to get an approximation for what that is. Sorry, just looking for, there we go, to the 1/3. So it says it's approximately equal to 4.76. See if I typed it in correctly. I mean, that looks believable to me. So it's saying that the slope of this line is about 4.76. So next week we'll get into examples where we have to, now I'm like doubting that. I'll check that math later. If someone else wants to check that and they think that's wrong, go for it. It just doesn't look as steep as being almost 5 to me, but whatever. Sorry, I can't get this to close. Yeah, anyway, so next week we'll get into more complicated examples where we'll see that we're going to use implicit differentiation in functions that also have like the product rule happening. So things like looking at the examples from the beginning. So things like this, right? Y times cosine of x, that's a product. Or even this one, 6xy is a product. So we'll see on Monday how to take derivatives of ones like that. All right, I hope you have a good weekend, and I will see you next week.